Today, I'd like to talk to you about our recent work towards magnetization-dynamics-driven superconducting pure spin current. This work was done in close collaboration with these persons by support from EPSIC program grant. Traditionally, dielectric spin transport studies in superconductor have involved in quartz particle injection at finite bias voltages around the superconducting energy gap. Several exotic properties mediated by quartz particle have been recently discovered. For instance, enhanced spin relaxation time, spin and charge separation, or giant spin Hall effect. On the other hand, equilibrium zero bias studies have focused on Josephson critical current in ferromagnetic Josephson junction and critical temperature tuition modulation in superconducting spin valves, which have demonstrated that static inhomogeneous magnetization configuration can generate long-range spin triplet pair correlation into ferromagnet. Nevertheless, dielectric observation of triplet spin transport through a singlet superconductor has not been demonstrated so far. In this talk, I'd like to describe a conceptually different approach, namely time-dependent ferromagnetic magnetization (FMR) can drive spin polarized transport through a singlet superconductor, highly likely be a spin triplet state induced by spin-orbit coupling. Let me first explain the basic concept of magnetization dynamics and resulting spin transport in a ferromagnetic Josephson structure, which is one of the most important elements in the superconducting spintronic devices. When the superconductor is in the normal state above its TC, the steady-state magnetization precession of ferromagnet can inject pure spin current into adjacent superconductors via dynamic exchange coupling across the ferromagnet superconductor interface, so-called spin pumping. And the absorption and dissipation of spin current in the superconductor leads to the enhancement of the effective Gilbert damping of ferromagnet, which describes how quickly the magnetization precession relaxes. On the other hand, in the superconducting state below the TC, when the superconducting energy gap opens, spin angular moment of magnetization in the ferromagnet can mostly transfer to the singlet superconductor through a quartz particle excitation. With decreasing the temperature, the superconducting gap and the energy of available quartz particle state increase, and thus the transport of dynamically driven spin polarized quartz particle becomes inefficient. This gives rise to the suppressed spin sink of the superconductor and thereby the reduced Gilbert damping of ferromagnet as compared to the normal state, as reported previously. In the following, I will present systematic set of temperature-dependent FMR measurement on niobium permanent niobium tri-layer with various niobium thickness, and show that, as expected, spin transfer from the precessing polymer into niobium layer through quartz particle excitation is blocked at low temperature by the superconductivity, and then extend the FMR measurement to platinum SFS platinum structure in which the platinum layer provides effective spin sink with strong spin-orbit coupling. When the platinum layer or other large spin-orbit coupling spin sink is present, significantly enhanced FMR damping below TC for the niobium layer thicknesses of the order of coherence length is interpreted as evidence for the generation of superconducting pure spin current. In our symmetric sample structure, spin pumping across permanent niobium double interface above and downwards improve the sensitivity of magnetization dynamics to the spin transport in the superconductors. In addition, superconducting transition temperature, which was systemically controlled by the niobium thickness, enable us to explicitly investigate the effect of superconducting correlation to the spin pumping and transport properties. We first confirmed dynamic exchange coupling between polymer and niobium layers of the sample by measuring FMR spectra as a function of niobium thickness using broadband FMR setup, which involves microwave source lock-in amplifier and coplanar waveguide at microelectronics group at Cavendish Laboratory. This figure shows typical FMR spectra obtained from the sample without the platinum layer at the fixed microwave frequency of 10 GHz at room temperature. As the niobium thickness increased, the FMR peak-to-peak line width directly proportional to the effective Gilbert damping increase, whereas the resonance magnetic field associated with the effective saturation magnetization varied little. This implies that dynamic coupling across polymer and niobium interface efficiently transfer spin angular momentum from the polymer into niobium layer, which enhance the effective damping of precessing magnetization. Next, let me describe how the superconducting correlation influences the magnetization dynamics and spin transport by measuring temperature-dependent FMR spectra across tissue. These figures show representative data for 3 different niobium thicknesses of 7.5, 30, and 60 nanometer obtained at a fixed microwave frequency of 20 gigahertz from 10 to 2 Kelvin. When the niobium thickness is 7.5 nanometer, which is non-superconducting in the range of temperature, the FMR line width varies slightly with the decrease in the temperature. In contrast, for the 30 and 60 nanometer, FMR line width is suddenly reduced by going through tissue, and the observed sudden reduction is more pronounced in the thicker niobium layer. This can more readily be seen by plotting the obtained FMR line width as a function of temperature for several different niobium thicknesses. For all niobium thicknesses, the FMR line width increases slightly monotonically with a decrease in the temperature from 100 down to 10 Kelvin. However, when temperature goes down further, noticeable reduction of FMR line width across tissue, which clearly depend on the niobium thicknesses observed after slight upturn. For the temperature dependence of resonance magnetic field, regardless of the niobium thickness, it decreases very weakly by less than 3%, implying that the effective saturation magnetization is almost independent of either niobium thickness or tissue. This indicates that the superconducting correlation is indeed responsible for the reduced magnetization damping below the tissue and thereby the suppressed flow of spin current. To quantitatively characterize this, we have plotted the obtained FMR line width as a function of niobium thickness for different constant temperature varying from 80 down to 2 Kelvin. For all temperatures, the FMR line width varied with the niobium thickness in approximately exponential pattern as expected from spin pumping and diffusive transport. However, when temperature is below 8 Kelvin, the FMR line width saturates faster to the relatively small asymptotic value as compared to the normal state. This means that below tissue, the spin transport efficiency diminished, as well as the characteristic length of spin transport in the niobium layer becomes shorter. For quantification, we have estimated two essential parameters of spin listening conductance and spin diffusion length, which govern the spin transport properties by fitting the niobium thickness dependence of FMR line with this equation. The estimated values are summarized in this figure. This result quantifies that in the superconducting state, the spin injection efficiency is reduced by approximately 25%, and the spin transport length dropped to approximately half of that in the normal state. The role of superconducting state in the spin injection and spin transport can be understood in terms of interface spin transference and diffusive penetration of spin polarized quartz particle, which is progressively suppressed with the decrease in the temperature. The transmission of non-equilibrium spin accumulation generated on the ferromagnetic side to non-magnetic layer depend on the matching of electronic band structure in two different materials on either side of the interface, which can be quantified as follows. We can then see that the spin transference for the permanent niobium interface is much lower when the superconducting is in the when the niobium layer is superconducting, supporting that the reduced spin injection efficiency is ascribed to the band structure mismatch due to the presence of superconducting energy gap. For the transport length of dynamically driven spin polarized quartz particle in the diffusive low temperature condition, one has to take into account the conversion time of quartz particle into singlet Cooper pair by angular refraction in addition to their spin lifetime. Considering that the conversion time is much shorter than spin lifetime due to the endoral refraction is fundamentally the interfacial conversion process. This equation can be simplified to square root division coefficient multiply the conversion time, which therefore can be comparable to the superconducting coherence length. In fact, we found that the estimated spin transport length of approximately 20 nanometer at 2 Kelvin is on the order of the zero temperature coherence length of niobium in the 30 limit. Let me now focus on the key result of this work. In other words, the suppression of dynamically driven spin current flow at low temperature by single pair correlation can be greatly modified when effective spin sink such as platinum is coupled with the superconducting niobium layers. This figure summarizes the obtained FMR line width as a function of temperature from platinum SFS platinum structure with different niobium thicknesses at the fixed microwave frequency of 20 gigahertz. The most important aspect of this data is the remarkable enhancement of FMR damping for the intermediate niobium thicknesses of 15 and 30 nanometer below TC when coupled with platinum layers. For the thinner and superconducting or thicker superconducting layers, the temperature dependence of FMR line width is qualitatively similar to the sample without the platinum layer. In contrast to the normal state, intriguingly, in contrast to the normal state, the FMR line width as a function of niobium thickness below TC cannot be described by standard spin pumping theory, indicating that notably different spin transport mechanism at work in the superconducting state. We also note that for the intermediate niobium thicknesses, the FMR line width and thus spin current flow toward the platinum layer is progressively enhanced with decreasing the temperature, not only in comparison with the other samples, but also in comparison with the normal state. The enhanced spin transfer cannot be carried by the coarse particle current because we have already demonstrated that they are progressively suppressed with decreasing the temperature below TC. Thus, the enhanced spin transport must involve superconducting current. The mechanism enabling supercurrent-mediated spin transport through a singlet superconductor are cross-endoral refraction, elastic co-tunneling, or induced triplet pairing state. These three transport mechanisms are previously proposed to explain the remotely induced magnetism in a normal metal in conjunction with superconducting spin valves, in which 70 nanometer thick gold layer is separated from the spin valve by 50 nanometer superconducting niobium layers. Of the three spin transport mechanisms, cross-endoral refraction and elastic co-tunneling via spin singlet supercurrent require the involvement of unpaired electron within the superconducting energy gap in both the ferromagnet and the spin sink. In order to distinguish between these mechanisms, we have replaced the platinum layers with a variety of other spin sink materials. The left figures shows the FMR line width as a function of normalized temperature for various spin sink materials obtained for the fixed niobium thickness of 30 nanometer and the fixed microwave frequency of 20 gigahertz. The right figure summarizes the spin sink material dependence of FMR line width change across TC. Here, positive and negative sign respectively indicate the enhancement and suppression of superconducting spin current in the superconducting state. Importantly, of the material used, a 5 nanometer tantalum completely proximity coupled to the niobium layer should be almost fully gapped and so eliminate cross-endoral refraction and elastic co-tunneling, whereas a 5 nanometer iron manganese weakly proximatized to niobium layer strongly suppress the niobium gap and thus makes this process more possible. The experimental result, which show that superconducting spin current is strongly enhanced by the tantalum and suppressed iron manganese, are incompatible with these processes. Therefore, the remaining possibility is the spin angular momentum is carried via spin triplet supercurrent. Several mechanisms for generating spin triplet pairing state have been proposed. For instance, static inhomogeneous magnetization configuration, spin-orbit coupling in the presence of exchange field, or precession of interfacial magnetization, because our sample structure contains a single homogeneous ferromagnet which precessing coherently, the first mechanism appears to be irrelevant. The second mechanism may be able to generate the necessary triplets state if we assume finite spin splitting in the fraction layer as supported by model calculation from our collaborators. Even if this model cannot yet quantitatively reproduce our result, our experiment on other material show that 5D heavy metal with strong spin-orbit coupling reveals a large enhancement compared to the other right elements, suggests that spin-orbit coupling possibly acting in combination with precession magnetization may provide the underlying mechanism. Last but not least, let me briefly introduce our latest work, namely a further improvement of superconducting spin current can be achievable by introducing spin-orbit coupled interface in between ferromagnet and superconductor. The idea is to enhance the total spin-orbit coupling induced triplet pair density without modifying the spin propagation between the ferromagnet and a superconductor by inserting a few nanometer thick interfacial layer which has strong spin-orbit coupling and modest spin diffusion length. Among a variety of materials which are intensively already studied in the field of room temperature spintronics, we have selected vanadium, chromium, and gold because they have large spin hole angle, 5 to 8%, and modest spin diffusion length beyond 10 nanometer. Our experimental data showing a further enhancement of FMR damping below TC for vanadium, chromium, or gold inserted samples suggests that superconducting spin current flow can be further enhanced by spin-orbit coupled interface engineering. This is the summary of my presentation. Thank you for your attention.